So, good day everyone. I am Cherry May Ruspo, and today I am going to tackle a continuation of a topic, metamorphism. So, in this presentation, we will discuss the types of metamorphism. Whereas the three types of metamorphism are regional, contact, and cataclysmic metamorphism. Next is the principal metamorphic rocks and their properties, where we will be discussing the six sequences such as speletic, quartzo-feldspathic, carbonate, calcareous speletic, mafic, and ultramafic sequences. And lastly, identification of magmatic, sedimentary, and metamorphic rocks. So let's begin. Types of metamorphism. As we all know that metamorphism is like a rock's makeover due to changes in pressure and temperature. The presence of specific minerals in a rock tells us about the condition it endured. So research reveals that initial materials can produce minerals based on environmental conditions such as aluminum silicate. Imagine the aluminum silicate as a starting material in rocks. Depending on how much pressure and heat it experiences, it can transform into three different minerals, and these minerals are andalusite, sillimanite, and kyanite. Determine metamorphism zones. As what you can see in figure 1.1, the three different mineral forms of the same substance, aluminum silicate, as a function of metamorphic condition. These minerals act as indicator, helping geologists understand the level of metamorphism a rock has undergone. Also, in figure 1.2, zones of alpine metamorphism determines by the mineral forms of aluminum silicate found in the rocks. In the context of metamorphism, zones essentially talking about the distinct level or stages of metamorphic transformation that rocks can experience. And geologists use these zones to understand the history and condition under which the rocks change. Metamorphic conditions are determined by the assemblage of minerals in rock, defining different facies like rim chest facies. This term refers to a group of rocks that has similar mineral combinations, providing more details about the environmental condition during metamorphism. Using an XY diagram, as you can see in figure 1.3, the three types of metamorphism, emphasizing the physical variables of pressure and temperature, we can define three principal categories of metamorphism: the regional metamorphism, or thermodynamics; contact metamorphism, or thermal; and cataclysmic metamorphism, or dynamic metamorphism. Let us discuss these types one by one. So the first one is regional metamorphism. Regional metamorphism is often referred to as thermodynamic metamorphism because it involves changes in pressure and temperature conditions over a large geological region. The term thermodynamic emphasizes the role of energy and heat in metamorphic process, and in regional metamorphism, rocks undergo transformation in response to changes in temperature and pressure following the principles of thermodynamics. So as what I've said, regional metamorphism, characterized by increasing pressure and temperature, is a primary type of metamorphism affecting large areas than magmatic intrusion or tectonic fractures, primarily resulting in metamorphic rocks. Just like in the diagram in figure 1.3, that shows a rock from their original state, like near the starting, to a more intense change form, even getting closer to melting. This makeover mainly occurs in big geological events like subduction zones or mountain building processes. Second, contact metamorphism are also known as thermal. Contact metamorphism happens near temperature axis as seen in figure 1.3, a thermal phenomenon found at depth or near volcanic chimneys or dikes. This local phenomenon creates contact aureole of rocks. Essentially, it's a thermal metamorphism, meaning it's related to changes in temperature or in which high temperature is the dominant factor. The zone of contact metamorphism is called an aureole. Furthermore, a metalliferous deposit was formed by contact metamorphism in a limestone rock resulting in a marble. High temperature magmatic fluid caused metasomatism, enriching the surrounding rock with silicate minerals, and this process may form rare polymetallic deposits such as copper near the intrusion. In figure 1.4, the specific example involved the alteration of limestone into marble and the enrichment of surrounding rocks with the virus elements forming distinctive mineral zones. The third one is cataclysmic metamorphism, or also known as dynamic. Mechanical pressures and tectonic fractures can deform rocks even at low temperatures, causing cataclasis and resulting in a fine crystal matrix, poorly aggregated debris or recrystallization. Based in Figure 1.3, cataclastic metamorphism occurs within fractures caused by tectonic activity. High pressures deform rocks without high temperature. So we have an example here. Cataclastic rocks like cacarite must be handled delicately in underground engineering projects to avoid collapse, earthflow, or worksite blockage. In Figure 1.5, we can see the texture of cataclastic tectonic microbichilia. Porous elements are caught in a very fine matrix with gneissic structure. In Figure 1.6, a tunnel boring machine excavating through cataclastic rocks. The low strength of these rocks coupled with groundwater cause of a collapse that blocked the machine. In simpler terms, when digging tunnels, there's a risk of running into fractured rocks that have been crushed or transformed by intense pressures. These rocks are fragile and can cause issues like tunnel collapse, making constructions challenging and potentially leading to delays. In this figure, we can see the three types of metamorphism in a subduction zone, whereas regional metamorphism, zones subjected to orogenesis and subduction zones, contact metamorphism, oriel around a magmatic body due to heat flow, and lastly, cataclastic metamorphism is at fault or overthrust zone. To sum up, the three types of metamorphism, ang regional metamorphism kay ginatawag siya nga thermodynamic because it involves changes in pressure and temperature. Ang contact metamorphism naman is ginatawag na thermal kay it's related to changes in temperature or in which high temperature is the dominant factor. Lastly, cataclastic metamorphism ginatawag na dynamic because high pressure deforms rock without high temperature. Moving forward, let us proceed to the principal metamorphic rocks and their properties. So metamorphic processes and initial rock origins generate numerous rocks, with their classification and nomenclature being complex due to their variety and complexity. The study presents the primary rocks resulting from regional metamorphism, defining sequences illustrating the gradual transformation of original material into rock, except for the ultramafic sequence. In Figure 2.1, it summarizes the things that we will be discussing, the six sequences of metamorphic, whereas the peletic, quartzo-feldspathic, carbonate, calcareous peletic, mafic, and ultramafic sequences and their metamorphism intensity. So the first one is peletic sequence. The peletic sequence, sensitive to metamorphic intensity, begins with clay and quartz particles forming a chemical stock with silicon, aluminum, and cations. Graduation into gneiss occurs at the end. So peletic sequence refers to a specific series of change that happens during metamorphism, and it discusses first because it reacts particularly to the intensity of metamorphic conditions. So in simpler terms, the peletic sequence describes how rocks made of clay and quartz change when exposed to increasing pressure and temperature. The result is the formation of gneiss, a more advanced metamorphic rock. Now let's proceed to slate. As metamorphic process act on this clay-rich starting material, it can lead to slate. So slate mineralogically transformation in clays forms haricite, a lustrous rock with a black color. It resists freezing and water content variations for centuries, breaking up into thin plates and weathering over time, making it rarely found in outcrops. So slate is a type of rock that often emerges from this transformation. It has lustrous appearance due to the micas, breaks into thin plates and is suitable for roofing. An example of this is in Figure 2.2, illustration of the schistosity of roofing slate. Next is chloride schist. Clay transformation causes chloride to appear, forming layered rock with sensitive texture and surface withering sensitivity, causing it to break up into foliated debris. In simpler terms, this rock formed from the metamorphisms of clays contains chloride and has a layered texture. It is prone to breaking into small pieces when exposed to weathering, highlighting its sensitivity to environmental conditions. So next one is mica schist. After chloride, phyllosilicates transform into micas, with quartz recrystallizing to form these continuous layers. Mica schists are stronger but easily broken during weathering, remaining finely schistose. So this stage in metamorphic process involves the transformation of phyllosilicates into micas recrystallization of quartz and the development of the schistose structure. The rock becomes slightly coarser, identifiable without a microscope, and gains strength due to quartz, while more resistant than chloride schist, it can still break up easily during weathering. The last one in phyletic sequence is the gneiss. Gneisses, a type of construction rock, exhibit recrystallization beyond quartz, forming continuous beds of light-colored minerals separated by phyllosilicates. They are strong and hard due to their quartzo-feldspathic framework. During the gneiss stage, the rock undergoes significant recrystallization involving quartz and feldspar. This results in a rock with continuous light-colored minerals bed separated by layers of phyllosilicate. Despite being foliated, gneisses are strong and hard, making them suitable for construction when found in massive formations. So in figure 2.3 is an example of mica schist. Chloride schist has a similar appearance with chloride replacing the black or white mica. So the next sequence will be quartzo-feldspathic sequence. The sequence comprises silica-rich initial rocks, including detrital, non-argillaceous, and non-carbonate rocks, which metamorphose into quartzites and felsic magmatic rocks that form gneiss. The sequence involves rocks that are rich in silica, a mineral compound. Let's proceed to quartzites. Quartzites are formed through metamorphisms of sandstones containing quartz grains and siliceous cement. As metamorphic intensity increases, quartzite evolves, but quartz grains continue to grow, making it difficult to distinguish between quartzite and magmatic quartz veins. Quartzites are white, ridge, and green in color and are found in thick beds in the Alps. They resist erosion due to their hardness and low physiochemical weathering, making alluvium highly enriched in quartzites. In simpler terms, quartzite forms a metamorphosed sandstones, becoming a homogeneous rock with increased quartz grain size. It resists erosions, but its hardness impacts drilling tools in specific conditions like tectonic areas with intense fracturing and groundwater. Quartzite can become unstable and flow. So this one. Gneiss is a type of metamorphic rock that can form in different ways. One way is through the intense metamorphism of a specific type of sedimentary rock called a pelagic sequence. Another way is from the metamorphism of felsic magmatic rock in the quartzo-feldspathic sequence. So in quartzo-feldspathic sequence, gneiss produced through intense metamorphisms of phyletic sequences or felsic magmatic rocks develops foliation with quartzo-feldspathic and mica layers. Orthogneiss, similar to sedimentary rocks, differs from magmatic rocks due to the anisotrophy. It is less stable in walls but has a good technical properties and is excellent building stone. An example of this is what you can see in figure 2.5. When ice is finely schistose, it can be used as roofing material. However, the slabs are considerably heavier than slate. The third one is carbonate sequence. Carbonate sequence is another metamorphic sequence that begins with limestone and dolomite as initial rocks with the purity of carbonates influencing the production of slightly different metamorphic rocks. If the limestone or dolomite is relatively pure, slightly different metamorphic rocks are formed through the process of metamorphism, where high pressures and temperature lead to changes in mineral composition and texture. The specific characteristic of resulting metamorphic rocks depends on the purity of the initial carbonate rocks. So now let's proceed to marble, which is under the carbonate sequence. Marble limestone transforms into marble at low to medium metamorphic intensities, producing homogeneous white crystalline rocks suitable for sculptures. Iron-rich horizons result in color-banded marble, with oxidation determining color. Dolomitic marble forms when magnesium content is high. Calcilicate marble form when limestone contains argillaceous or quartz impurities, occurs in layers or variable thickness, and behaves ductility at high pressure. So in figure 2.6, we have examples of marbles. In letter A, sample of very pure marble, and letter B, you will see the marble quarry, open pit quarry cutting and removal of blocks. So in addition, marble with its hardness similar to calcite is used as ornamental stone and can be calcified in acidic water. It is also used in the construction industry for decorative polished rock and artificial aggregates of colored rock. So in simpler terms, marble is a beautiful and versatile rock that can come in various colors and patterns. It is used for sculptures and ornamental purposes, but its susceptibility to dissolution in acidic water should be considered in certain geological contexts. The term marble in construction may not always refer to the geologically defined rock, but rather to any polished and decorated stone. In Figure 2.7, you will see the method of cutting marbles block using diamond cables. So the fourth one is calcareous speletic sequence. Marls, which are mixtures of limestone and clay, are the point of departure for this sequence. A calcareous speletic sequence refers to a geological sequence or rock formation that consists of alternating layers of calcareous, calcium carbonate-rich, and peletic clay-rich rocks. The term calcareous is derived from calcium carbonate, which is mineral commonly found in rocks like limestone and marble. On the other hand, peletic refers to rocks rich in clay minerals. So let's proceed to calcist. The rocks are finely layered, schistose, slightly metamorphosed, with calcite recrystallizing, like marble separated from schist layers from clay. They are weak, anisotrophic, and slightly permeable. Its composition involves recrystallized calcite, resulting in competent layers, but it remains a relatively weak rock, and its properties can vary depending on the directions. It's also highly permeable, allowing some fluid movement through it. Now let's proceed to amphibolite. Metamorphism intensifies, releasing carbon and forming feldspar and calcic amphibole prisms. Amphibolite, a schistose structure, is composed of fine layers of amphibole and feldspar. In simple terms, as rocks undergo more intense metamorphism, they go through chemical changes, losing carbon and gaining new minerals like feldspar and calcic amphiboles. The resulting rock amphibolite has a layered structure with alternating layers of amphiboles and feldspar. This layered arrangement is what gives its schistose structure. So in figure 2.8, you can see an example of calcist, the cold and Olin calcist. So the fifth one is mafic sequence. Prograde metamorphism affects mafic magmatic rocks, recrystallizing and orienting minerals without altering the original matrix, resulting in preferential orientation of ferromagnesian minerals and anisotrophic structure. A mafic sequence undergoes changes in its mineral arrangement and orientation due to prograde metamorphism. The minerals, particularly dark-colored ferromagnesian minerals, become aligned, resulting in a rock with a preferred orientation and an anisotrophic structure. Despite these changes, the overall mineral composition of the original rocks doesn't undergo significant alteration during its process. So amphibolite, mafic rocks subjected to metamorphisms have a banded texture consisting of calcium-rich plagioclase layers and luminous green amphibole layers, making them more massive than the calcareous speletic sequence. Mafic rocks often found in the Central Alps undergo retrograde metamorphisms, turning into prasinites rich in albite, epidote, and chlorite, which are slightly anisotrophic due to phyllosilicates and susceptible to surface alteration. So in simple terms, amphibolite is a banded rock formed from the metamorphisms of mafic rocks. When these rocks undergo retrograde metamorphisms in mountainous regions like the Alps, they transform into prasinites. Prasinites have distinctive white spots, albite, or this is what we call the albite, a green matrix or the chlorite, and a slightly anisotrophic nature. They are susceptible to changes at the Earth's surface. So, as you can see in Figure 2.9 amphibolite, Swiss Alps, and in Figure 2.10 you can see the example of prasinite. So the last sequence will be ultramafic sequence. Ultramafic rocks originating from mantle experience significant disequilibrium with folded onto mountain chains, leading to retrograde metamorphism in this environment. So in other words, ultramafic rocks originating from the mantle and rich in minerals like olivine and pyroxenes go through a state of disequilibrium when folded into mountain chains. This leads to retrograde metamorphisms, where the rocks undergo changes due to decreasing pressure and temperature in this mountainous environment. So serpentinites are deep origin rocks made of unstable ferromagnesian silicates, which undergo a transformation to serpentine when moved into upper crust. These rocks are deep green, almost black in dry state, and have low strength in underground construction due to tectonic shearing polished microsurface. So we have an examples here in figure 2.11, highly tectonized serpentinite. So now we are almost done. The next one is identification of magmatic, sedimentary, and metamorphic rocks. Identifying rocks using various methods and techniques including attentive observation and easy to apply field techniques. Petrologic identification equipment includes a steel scraper, glass plate, dilute HCI for carbonate rocks, and a hand lens for minerals. So rocks are broadly categorized into three main classes: magmatic, sedimentary, and metamorphic. Geologists use various methods and techniques for a rock identifications. While these methods can be diverse, the focus here is on simple observation and field techniques. To identify rocks, geologists use a combination of observation and basic field techniques. They pay attention to the typical features of each rock type. Tools like steel scraper, glass plate, dilute, and a hand lens help in assessing hardness, characterizing carbonate rocks, and closely examining mineral details. While more advanced techniques exist, these basic tools or observes are accessible for initial rock identification in the field. So, diri na part is diri makita nato ang mga kung unsang mga pangutana or unsang mga questions in determining kung unsa na siya nga type of rocks para ma-identify nimo if either magmatic, sedimentary, and metamorphic rocks. So in figure 3.1, it is a series of questions in order to identify what type of rocks, either magmatic, sedimentary, and metamorphic rocks. So in this slide, in this figure 3.2, it shows the petrological determination flowchart. By systematically following this flowchart, the reader will find a rock or rock category. At this stage, the reader is advised to verify the likelihood of the result, and if it fails the test, you should try other possible branches of the chart. This simplified determination method is useful for common rocks showing their typical features. So that's end our presentation, and now let's have a quick review for the following that we've discussed today. To sum up the three types of metamorphism, ang original metamorphism kay ginatawag siya nga thermodynamics because it involves changes in pressure and temperature, and contact metamorphism naman is ginatawag na thermal kay it's related to changes in temperature in which high temperature is the dominant factor. Lastly, cataclysmic metamorphism ginatawag na dynamic because high pressures deforms rock without high temperature. Next one is the principal metamorphic rocks and their properties have 6 sequences, and those are palatic, parts of feldspathic, carbonate, calcareous palatic, mafic, and ultramafic sequences. Palatic sequences nagadescribe siya on how the rocks made of clay and quartz change kapag ma-expose kini sa increasing pressure and temperature. Parts of feldspathic naman kay involves a rock that are enriched in silica, a mineral compound, and a carbonate sequence naman is where high pressure and temperature lead to changes in mineral composition and texture. Calcareous palatic sequence kini nga sequence kay nag-refer sa rock formation nga naga-consist of alternating layers of calcareous, calcium carbonate rich, and palatic clay rich rock. The term calcareous palatic derived from calcium carbonate, and palatic naman is nag-refer sa rock nga rich in clay minerals. Ang mafic naman kay nag-undergo sang pagbago sa mineral arrangements due to prograde metamorphism. And lastly, the ultramafic nag-originate from the mantle and reach in minerals and go through a state of disequilibrium when folded into mountain chains. And the identification of magmatic, sedimentary, and metamorphic rocks naa dito gihatag nga a series of questions and a flowchart para ma-identify nato of what type of those rocks it's either magmatic, sedimentary, and metamorphic rocks. And also, in conclusion, metamorphic rocks are a rich group of rocks that engineers encounter in their work. To understand their exact nature, engineers should identify the original rock, consider the compositions and properties due to history, and consider their anisotropy. An analysis of their stability should consider the geometry of the engineering project and laboratory test interpretation. So that's all. Thank you for listening, everyone. Once again, I am Cherny A.